Okay, good afternoon, everyone. Thank you very much for being here with us in another seminar here at the Astronomy Department of the IAG. Today, I'm really pleased to present Marc Armah. Thank you very much for being here with us, presenting your work. I will very briefly introduce him. Marc got his bachelor degree in mechanical engineer from the University of Mines and Technology in Ghana. And then he transitioned to astrophysics, completing his master in physics and astronomy at UNIVAP. And he received his PhD in astrophysics from the Universidade Federal do Rio Grande do Sul last year. And currently, he's a FAPESP postdoctoral researcher at UNIVAP. So, Marc, whenever you're ready, you can start.
Thank you for the introduction. I believe you can hear me. Okay, thank you. I don't need any further introduction, so I will proceed with my presentation for today. I'll be talking about identifying AGNs from X-ray detections, resolving systematic biases in metallicity calibrations. So I'll begin with a brief review of the methodologies for metallicity derivation. Basically, we have two basic methods, the direct method and the indirect method. But before I proceed with that, if you see the term metallicity, we normally measure it in unit of 12 plus the log of the oxygen per hydrogen abundance, or in this format. And it has been like that. So if you see it in this unit, that's fine. If you don't see it and you see it in decimals, then definitely it is in this form, in solar unit. So before I even proceed with the direct method, I would like us to look at the reasons why we do what we do. Like some of us study the gas phase metallicity in galaxies, because between the age of the universe, from about 200 to 400 million years, the universe had no metals. And so we look at this, which normally refers to as the ladder of decreasing metallicity, from where the universe had no metals up to some of the observations we've made from the most metal-poor galaxies up to the most metal-rich, if we can put it that way. Then I also like to show something here. This is the normal periodic table to probably all profession, but to us who study metallicity, it is hydrogen and helium. Everything else to us is metals. Now, going back to the decreasing ladder of metallicity, it is important for us to know the first metal-free stars, normally known as the POP3, or the most metal-poor galaxies, mostly the dwarf galaxies, as we know. And it will be interesting for us to understand how they look like, all the properties about them, so we can understand the evolution of most of the low redshift galaxies we have. So it is the most important thing, and then basically it all surrounds around galaxy evolution. Now let's move on to the foundation to the metallicity, looking at the direct method. The direct method evolved around detection of auroral lines. And to have these auroral lines, I have a spectrum on my right, which shows surface, liner, altogether AGN, if we look on the BPT diagram, which I will show in subsequent slides, and then the H2 region. It is interesting to see that the auroral lines, example of oxygen 4363, which is required to directly measure the electron temperature, it's mostly very weak in metal-rich galaxies or far infrared or higher redshift galaxies. And so once it becomes difficult to detect the auroral lines, then we need to have an alternative way of estimating metallicity, because we are in the age of huge amount of observation with a lot of data. And if you look at some of the surveys, the best we can do with the auroral lines or the direct method will be around probably 20% when you have a huge data set. And so we have to find an alternative way of deriving the metal content of all of these galaxies by considering the strong emission lines without, bordering with the auroral lines, which gives us a lot of problems to detect. So basically, as I talked about the auroral lines, we have the strong nebular lines here, which can easily be detected, and we can rely on them for the indirect method, whilst we have the auroral lines very difficult to detect. And so I show a typical spectrum. As we can see all the emission lines here, look at the zoom in for this auroral line. Without the zoom in, it is almost impossible to see it. But when we zoom in, then we know the line is actually there. However, we don't even need to zoom in for some of these things. We know they are there. And if you compare this even to the H-beta, the H-beta appears to be about 100 times stronger than the auroral line. So this is the reason why we look for other alternatives, like the indirect or the strong line method. Aside being difficult to detect, if you compare the metallicity from the direct method or the TE method to the other method, the TE method underestimates the metallicity. If you look at the histogram distribution here, it underestimates the metallicities in AGN. So coupled with this reason, it is important for us to rely on the indirect method to actually derive the actual metallicity. So I'll briefly talk about the strong line method, which basically has about 4 different types. But my presentation today is centered on the first method, which is known as the hybrid. The hybrid involves a combination of observational data and theoretical models, which we normally use clouding to derive. Then we have the empirical, which basically relies directly on the TE method. And then we have the pure theoretical, and then we have the recombination weak line. So basically my presentation will be centered around the hybrid method. Now, moving into the hybrid method, there is a huge degeneracy in the models, because up until this particular work, there has not been any calibration which doesn't rely on the ionization parameter, which is known as the U. And one challenge with this ionization parameter is that we put the ionization parameter in the model to derive or predict the emission lines. However, the emission lines themselves are dependent on the ionization parameter. So as you see here, this is a plot of the ionization parameter versus the oxygen 3 versus oxygen 2, which is most importantly determine the ionization degree of the ionized gas. So if you are using U to predict the most important emission line ratios that we need, then how can U be reliable to us? So this is the reason why we are moving away from using U, and we are going to substitute U for the X-ray luminosity and see how it turns out. So that is recently the work that I and some other groups have been working on. And it is known there are a lot of biases, but I just picked this one coming from the ionization parameter about 0.7 dex. So now the model shift. These are basically most of the important input parameters in any model that you can run with a log of U. So in the current work, we are replacing U with the log of Lx, which is the X-ray luminosity. Now, let me go back a little bit. If you look at the ionization parameter, it determines, it relies on the radius. It's inversely proportional to the square of radius. And because of this, the U is also directly related to the luminosity. And if you vary the radius, what you are doing is that you can have 2 scenarios where you can have the same ionization parameter, with different combination. For instance, if we have a low radius or a small radius and then a low luminosity, what it means is that the gas to be ionized is closer to the source. And this gives you the same result if you have a larger radius and a higher luminosity, which contribute to the degeneracy in the metallicity as we know it. So to move away from this and using the X-ray luminosity, we have to fix the radius. But what is a reasonable value and how will this assumption impact the calibration? So we run the model and then we rely on the gravity calibration observational determined ratios. So for the gravity calibration, they derived ratios in the range of 0.028 up to 1.33. And then they also derived the relation where the radius is inversely directly proportional to the square root of the X-ray luminosity. So we have three different things. And then we benchmark it against our baseline radius that we assume in the model, which is about 0.3 parsecs. Now, if we after varying all the different radius and then comparing it and estimating the metallicity with our baseline, considering all these four indexes, metallicity indexes, the first two has to do with the first paper that we've published, and then the second two is based on the calibration we derive, and it's a submitted paper currently under review. So when we compare the different radius together with our baseline, we realize that the systemic variations, it's within acceptable range, because there are no two calibrations that are the same, but there are some acceptable range. From the literature, the maximum we have seen is about, when you compare the direct method to the indirect method, it's around 0.2 dex. However, if you compare different calibrations, it can go up to a range of from minus 0.1 up to about 0.8 dex. So having all the systematic differences even way below 0.2 dex means our assumption of 0.3 parsecs, it's great and it's working good for us. But it doesn't also necessarily mean we can just decide to pick any radius we want. It doesn't work like that. Okay, so to move on to compare the model parameters together with the observation, we need to determine how luminosity varies or predicts or relate with ionization degree. So here I show 4 columns of 4 panels of diagnostics with the luminosity versus the ionization degree, and then color code it with all the model parameters that we use in our models. Now, we obtain these values by interpolating the observational data point onto the center or the ionization space of the observational data. So from all this, what we can say is that the models are behaving directly just as the observational data. So to go on, we used observational data from the bus data release 2. So we have, these are observational data. We have the luminosities for this. We selected about 617 surface galaxies from the BPT diagram. And then we know the luminosities of these galaxies. And so we can, once we know the luminosities, we can predict this luminosity from the models, and then we can compare or combine them in a hybrid or a semi-empirical way. So this is just an example of how the models behave. In the columns, we are varying the SED, the spectral energy index distribution parameters, and then across the row, we are varying the density. So we start from a density of about 10 to the power 2 to 10 to the power 4. And then we move also from a spectral index of minus 0.8 up to minus 2. But we realized that the models are able to reproduce the observational data from minus 0.8 up to minus 1.4. Beyond that, the models kind of overlap on each other, and then when you do the interpolation, it becomes very difficult to derive the metallicity. So we limit it up to minus 0.8 up to minus 1.4. And as I explained earlier on, we built models of about 6,300, and then out of the 617 selected AGN surface 2 nuclei from the bus data, we had, because we have to derive the ratios, we have a high quality for 426. Okay, so let me go back. So this is just for one of the indexes, that is the N₂, against the ionization degree. And then we look at the O₃N₂ also, which appears to be a little bit of improve on the N₂ parameter, which is as a result of the expansion of the volume in the partial ionization zone as a result of the X-ray photons, which I will demonstrate and then provide better explanation as we move along. Okay, so now this is the two final calibrations we derive. In here, we color code all the interpolated values considering the model parameters, but our focus is on the X-ray luminosity. So if you look at the third row, the N₂, we have a huge scatter within the interpolated value, as well as the O₃N₂ index. And these variations, we will see later on, translate directly into the individual differences within the metallicities. So we have a range of 3 ranges of X-ray luminosity, and these variations lead to a maximum of about 1.0 dex in metallicity difference. So after combining everything, we derived a combined calibration for the N₂ index and then O₃N₂ with a huge metallicity discrepancy of 1 dex. But this is not a systematic difference. It's just as a result of, if you look at the highest luminosity deviate from the mean luminosity value. So this is coming from the most extreme luminosity values. So, but systematically, if we compare the metallicity derivation from the two calibration, systematically we have a difference of about 0.11 dex. However, if you look at the individual differences, you will see that 1 dex difference, about a maximum of 1 dex difference that we see in the vertical variations reflect in the individual difference when you compare metallicity from the two calibrations. Because if you look at the difference, it could reach about 1 dex. However, systematically, we have 0.1 dex. Okay, so now we have to contextualize our result or benchmark it against the existing literature. Sorry, I didn't define these abbreviations, but this is a theoretical based calibration. There's a huge difference between this calibration and our derivation from about 0.3 up to 0.7 dex. Now, when we compare it to this, and all these calibrations you are seeing used ionization parameter. This is the first time we have derived calibration with the X-ray luminosity. So you can understand why we are having this kind of differences. And moreover, the SED that was used in this calibration was very low values, closer to stellar-like SED as compared to the hard X-ray SED that you might normally use. So it's not surprising we are seeing this kind of difference. But interestingly, this calibration happens to be, very close to what we derive. And understandably, because this was also based on the N₂ index, and then we compare N₂ index to N₂ index. So it is also not too surprising. But we have a little bit of higher when you compare it to the other calibrations, as well as a huge difference between this, because this is also empirical based on the TE method as expected. The abundant discrepancy factor reflects in this method because this is basically from the TE method. Okay, so now let's move on to the second phase of the project, where we consider this N₂O₂ and N₂S₂ calibrations, and we see a huge improvement if you compare it to the previous one. If you focus on the third row, you see that the huge deviations we saw in the previous calibrations have been diminished in this second phase of the project. And the reason is simple. It's because if you look at N₂ and O₂, they have a very similar ionization potentials. I think the nitrogen has about 14.56, and oxygen has 13.63, if I'm right. However, if you look at sulfur has about 10.36, which is a little bit of huge difference from that of the nitrogen. So looking at these two calibrations, the numerator is the same, the denominator is the difference. So the difference comes down to the oxygen 2 and sulfur 2. Now, we are seeing a little bit of deviations within the X-ray from the S2. Why? This is happening because the critical density for sulfur is very low. So as we move to higher density, de-excitation seems to affect the sulfur line. And so we attribute this huge deviations to the de-excitation and because of the critical low density of the sulfur emission line. And so we derive a root mean square of about 0.08 and then 0.012 for the sulfur, which is a huge improvement from the previous one, the N₂ and then N₂ calibration. Now, so for the physics behind the N₂O₂ and N₂S₂, we have to look at how the ionization happens when we are using the ionization parameter as well as the X-ray luminosity. Okay, so in these three panels, we vary the ionization parameter from -3.5 up to 1. Now, as the ionization parameter value increases, we realize that even before that, we can see that the oxygen 2+ happen to saturate earlier when we move from lower ionization values to higher ionization values. And we also realize that in the outer part of it, where we have the partial ionization zone, we also realize that the log of U tend to behave differently from that of the X-ray luminosity, which I will just show here. So this is the X-ray luminosity variations. Now, we look at the inner part of this, and the behavior is very similar. It's almost the same. The difference is the normalized radius as we see it here. This is all happening because of the hard X-ray emission that is causing this to happen. And the reason why, and this also explains why in the N₂ and then O₃N₂ calibration, we find those huge variation. It's because in those calibrations, we do not have similar ionization potential from two elements, where you divide and then they kind of cancel out the X-ray effect that is as a result of expanding the partial ionization zone. But over here, because we are dealing with the N₂O₂ and N₂S₂ coexist in the partial ionization zone, and they have similar ionization potential, they tend to cancel out the X-ray effect which exists in the previous two calibrations. So I just put them side by side, and then I also did a kind of a toy model to properly demonstrate how and what is actually happening here. So I think if we focus carefully on all the values, you realize that we have metallicity here, we have the density here. As we move towards the gas cloud, if you pay attention, the metallicity varies, the ratio remains, the ratio varies with changing metallicity, but with changing electron density, the ratio remains constant. It is the opposite here. If you pay attention to the N₂S₂ ratio, it changes with electron density and then the metallicity as well. Whereas the N₂O₂ remain constant with a changing electron density. Why? Because they are not so much affected by de-excitation as I tried to explain earlier on, but the sulfur is highly affected by de-excitation, and that is why we saw a kind of appreciable, it's not too significant, but if you compare the two calibrations, the N₂O₂ tend to perform better than the N₂S₂. Okay, so from those two calibrations too, we derived semi-empirical calibration for the N₂ index and then for N₂S₂ index. Now we compare all the four calibrations. And then this was the first two calibrations we derived. Now we compare each of the calibrations. And then if you check all the comparison, you realize that for the systematical difference is very minimal. But if you look at the individual differences, if you compare N₂O₂ and N₂S₂, you realize that whenever we have N₂S₂, take for instance, here we have N₂S₂ versus N₂. So there's already a huge systematic difference between the N₂. So whatever we compare with N₂, we have the individual differences going very high. Now let's look at N₃, no, this is N₂O₂ and then O₃N₂. Look at the systematic difference and even the trend. It's almost flat. It appears to seem these two calibrations are tracing almost the same metallicity. And the same way, if you look at the N₂O₂, even with the N₂S₂, you see a huge individual differences, especially for the extreme X-ray luminosities. So from this comparison, we came to the conclusion that from all the emission line ratio indexes that we derived in this project, the N₂O₂ stands out to be the best. So if we have the blue emission lines for the oxygen 2 and nitrogen 2, why not? We should use it for the metallicity. Other than that, the N₂S₂, it's equally suitable to estimate the metallicity. Okay, so now we compare those two new calibrations with the literature. We compare it with the TE method, we compare it with the theoretical. The theoretical calibrations are two. So we have the SB98-1 and then the 2. And then the N₂ calibration as well as the empirical calibration. And the differences, systematic differences are the same with the N₂ and then the O₃N₂. It's very similar. Okay, so now moving forward, we are also working on this, trying to improve the various differences that we have seen even though the systematic differences are within reasonable, but we still have the opportunity to reduce them. So we are trying to unify all the various emission line ratios. Now, interestingly, we improve on all those two. I can go back to the first calibration we derived, and you look at the difference. Let's pay attention to just the X-ray row. And then we come back to the second one that we derived. Oh, sorry. Okay, the second one, we also look at it. There was an improvement based on the similar ionization potential between these emission lines. Now, with a combination of the various line ratios, we see a huge improvement. If we look at the N₂, we have improved it by about 6 times, I believe. And this has been improved by 2 times, and then each of this by 4 times, by considering different variants of ratios, and then running a lot of simulations with the models to determine the best fit coefficient, and then unifying them to estimate the interpolated metallicity with the same ratio. So this is a work in progress. We haven't decided finally on this, but in the preliminary result that we are seeing, it's a huge improvement within the various calibrations. Okay, so this is where it will even be very clear to see. So here I produce the global fit parameter that we use to derive all the calibrations for the N₂, and then for the O₃N₂. The root mean square is about 0.22, and this is about 0.20 because it's a run up to 0.205. Now, we can just compare this to the second one, I believe. And this is, okay, this was the first calibration, this is the second calibration, and this is the unified calibrations. So over here, it is obviously clear that there has been a huge improvement. There's a huge scatter in this, which translates directly into the metallicity estimate. The scattering minimized, as I explained, similar ionization potentials, and then with a combination of the variant, we are seeing a huge improvement. So even though there's still systematic differences, but the X-ray luminosity in the models seems to be performing better, and then as expected, of course. So I think I would like to acknowledge some of the people that I've been working with on this project. Here is my master's and my current postdoc advisor, my PhD advisor in UNIVAP, my PhD advisor in Porto Alegre, Rogelio, and then Monica and Guillermo in Argentina, Hujama in Santa Maria, and then Pepe in Spain. So I'll end my presentation here, and then I'll be ready to take any questions you have for me. Thank you.
Okay, thank you very much, Mark, for your talk. So we're open for questions. No, I thought you were. I'm sorry.
So you arguing that N₂O₂ is a good indicator, a good tracer, but it's very sensitive to dust.
Yes.
So I'm wondering if that the improvement you gain from the physics itself is not
Okay, so all these calibrations were derived before we even start the derivation. We have to correct for we have to undertake reddening correction. So we apply reddening correction. Okay, I think I have some extra.
I mean that in practice you'll have to correct it for dust, and that maybe you lose its power because of the uncertainties in that correction. That's what I mean.
Not necessarily, because you see, we are driving the calibration with a kind of a uniform way, even though the emission lines are different. But basically, the N₂O₂ is doing well because of one, the similarity between the ionization potential, as I explain later, it's about 1 or point something. And then the X-ray luminosity expand the ionized volume. And then when you also find the ratio, the effect of the X-ray is cancelled out, obviously. But, okay, so let me kind of go back. Let me come back to this. Okay. So we have the N₂O₂ and we have the N₂S₂. You agree with me that the S2 suffers from collisional de-excitation as we move to higher electron density, but we don't see that here because the critical density for oxygen 2 is higher than the critical density for sulfur 2. So it is not too surprising that N₂O₂ seems to be performing better than almost all the calibration. Why? Because if you look at the N₂ alone, standing alone, cannot cancel out the X-ray effect that you cannot even find in the other calibrations which use only the ionization parameter. If you use only the ionization parameter, you may not see the X-ray effect, and you may misinterpret the metallicity as a higher metallicity, but it is not. You may derive a higher metallicity from the using ionization parameter calibration, but it is an artificial value because of the expansion of the X-ray. But over here, we see the effect, and the effect is dealt with.
Okay. The other question I had isn't N₂O₂, because of the, you mentioned the similarity of the ionization potentials?
Yes.
So I always thought the N₂ divided by the O₂ is basically N over O.
Yes.
So are you fixing any N over O in your runs, or how do you deal with the nitrogen to oxygen abundance ratio? Because if that's fixed, or is that, you have to assume something in your model.
No. The model parameters are the same for all. We run one model. Okay, so all these calibrations are derived.
So if you twice solar metallicity, you have twice nitrogen and twice oxygen.
Yes, but all these calibrations are derived from the same models. Like we use, so let me go back to, okay. So we run the model with the X-ray luminosity. The result we have, we use the result for the same input parameter. We do not run a special model for N₂, a special model for O₃, N₂. No, it's the same model. And out of the same model, we derive the calibration for all the 4 index. But there are other chemical chemical ratios, like the N₂ ratios, which I did not show here. But if you scan the QR at the end of my presentation, sorry, those relations are in this newly published paper. If you scan the QR code, you can read the paper. We have the abundance ratios for helium, for nitrogen over oxygen, and then we fixed almost all the other to the solar value. But the input parameters are the same for all calibrations. Yeah, but I take your point. The N₂O₂ also rely on the chemical abundance ratio to plays a role. But not only that, the N₂S₂ also is also affected by the same chemical abundance ratio as well. Yeah.
Okay, thanks.
Okay, do we have more questions?
Thank you for your presentation. I just have a quick question. Your models was based on X-ray luminosity.
Yes.
So it's just a calibrator for AGN population.
Yes.
And not star forming.
No.
Thank you.
It's not star forming because yes, because we are using the AGN SED slope and not star forming from either starburst 99, but we can try that, but this is purely AGN SED.
Another quick question. Did you observe in your calibration analysis any bias towards a given population, let's say Seyfert galaxies versus radio galaxies, or because essentially the analysis, your sample is for luminous sources, but
yeah. Thank you for the question. Okay, so for all the observational data that we used are confirmed surface 2 galaxies. I'm getting this wrong all the time, sorry. So they are all confirmed surface 2 galaxies. These are the luminosity range. These are the observational data, and this is their position on the BPT diagram. So they are all surface 2 nuclei. Yeah, but we derive. See, if you look at this in the paper, we present calibration for each luminosity range. So you can as well, if you like, if you know the X-ray luminosity of your galaxy, you can pick one of the calibrations for the luminosity range, and then you estimate the metallicity, and then you can compare it to the overall metallicity derived, and then you can decide for yourself. Yeah, you can also do that exercise if you know the X-ray luminosity of your galaxy. Yeah. But we didn't, with this work is entirely limited to surface 2 nuclei. We haven't considered any other AGNs. Yeah. Yeah. Because liners also have different luminosity, and I have a BPT diagram, but I'm not using my computer. I would have shown you. We actually positioned liners from dwarf galaxies on this diagram and on this diagram, and it is interesting to see the positions of these two galaxies. So for now, we are focused on the surface 2 nuclei. Maybe in the future, we can look at other class of galaxies.
More questions? If not, let's thank the speaker again. Thank you very much. And please join us in the coffee break so we can discuss more with Mark.